Hi, I'm Fernando Pereira from UFMG, and today we will see our last example of a data flow analysis. Before we try to summarize them all into a single theoretical framework, Anyways, this last analysis is called reaching definitions. To explain what is reaching definition analysis, we shall use this program. As before, the question is the same. How can we optimize this code? This example is rather tricky. Would you like to stop the video and think about the program? Try to figure out how this code could be optimized. This assignment, z get z minus 1, is dead. By that I mean that the definition on the left side, which is z, is not really used anywhere. Mind it that I'm saying that the definition, not the variable z, is not used anywhere. That's very important, for the name z is indeed used, but the variable defined and the red box is not used anywhere else. Can you try to think about ways to find out that definitions? In this case, do you know why the definition of z in the red box is dead? Usually, it's easier to see opportunities for optimizations in the CFG. Let's take a look into the CFG of this program. Here it is, the CFG. Notice that we have two definitions of z, one at D5 and another at D8. The definition at D5 reaches a use of z. I'm showing this def-use relation here with the arrow. But the definition at D8 in third doesn't reach any use of variable z. That's why we say that the definition at D8 is dead. But the definition at D5 is not dead, only the one at D8. Here you have some useDef chains. These are relations between points where variables are defined and points where they are used. And as you can see, there is no arrow leaving the definition of Z8 at D8. So we say that a definition of a variable v at some program point p reaches a program point p prime if there exists a path on the CFG from p to p prime and this path does not cross any new definition of v. That's pretty similar to liveness, right? But it's different too. Can you remember the difference? And now that we have defined reaching definitions, do you know how we could compute this analysis? Can you think about what would be the information that we would be recording? And how this information would be transferred? Indeed, there are many questions that must be answered to construct this analysis. I'm leaving a few questions to you in this figure. If you want, before we move on, you can stop the video and then try to answer these questions. If you want, of course. I shall be providing answers shortly anyways. So let's start with the origin of information. If we have a definition of a variable, call it v, at a point p, then we know that this definition reaches the point immediately after p. That's because there was no time yet for any redefinition of v to be met. So, information originates on points where variables are defined, and it propagates forwardly. But there are other ways to propagate information in this analysis too. All the definitions that reach the point immediately before p also reach the point immediately after p, as long as p does not redefine these definitions. So again, this is a forward analysis because information flows along the same directions as the edges of the program's control flow graph. But how do we join information in this analysis? What if a program point has multiple predecessors? In other words, how do we compute the set of reaching definitions immediately before this join point in the program? In this case, we use the union of reaching definitions. So it suffices that one definition reaches the point after some predecessor to reach the point before p. In other words, we do union of reaching definitions to compute the merged information. And as in the previous analysis, we can save data flow information in the in and out sets. We have one in and one out set for each instruction. In is the set of definitions that reach a point before the instruction, and out the set of definitions that reach the point after the instruction. Here you have an example. Take a look into this program. You can see the different definitions of variables y and x. Notice that data flow facts are program points like P0 and P1. We don't use the names of variables because the same variable can be defined at different program points. So we represent definitions as program points, assuming that every program point defines a single variable name. Anyways, can you think about the equations for this data flow analysis? If you want, you can try to stop the video and try to transpose the equations that we had seen before to this new setting. Here you have them, the equations for reaching definitions. If you want, you can take a look into them. If you want, you can stop the video. However, notice that we are representing data flow facts as pairs here. Each pair is formed by a program point plus a variable name. In this way, our analysis supports programs with multiple definitions and the same variable name, and program points in which multiple different variable names can be defined. Notice that definitions create information immediately at outsets. Also, notice that definitions kill older definitions of the same variable. In other words, the definition of a variable v never crosses points where v is redefined. And finally, notice that we use a union to join reaching definitions at join points in the code. As an exercise, if you want, you can try to run reaching definitions in this control flow graph. If you want, you can stop the video, draw the program, and then try to fill out reaching definitions on the edges of the CFG. Here's the solution to this problem. Because each program point defines just one variable in this program, I'm using the program point itself as the data flow fact. So instead of a pair formed by a variable plus program point, I only record the program point because the variable can be inferred out of that information. And how can we use the solution of this data flow analysis to know that the definition of variable z at D8 is dead in this code? I'll leave this last question as an exercise to you. It's a simple answer, but if you want to know it anyways, just ask me in the comment section of the video. And that concludes our explanation about reaching definitions. In the next class, we conclude this overview of data flow analysis. I will be introducing something called the monotone framework, which is a general way to reason about data flow analysis. Till there, you feel free to write me with questions and comments.